If you were in possession of a secret code, how would you crack it? How could you use statistics to read your friend's messy handwriting? One approach is to use the relative frequencies of letters to determine the message statistically. In terms of relative frequency, E is the most common, followed by T, A, O, and I, with Z being the least frequent. We sought to test the letter frequencies published in Robert Lewin's Cryptological Mathematics, which describes how statistics can be used to crack ciphers. We chose to test these frequencies using State of the Union addresses, since they were all written for Congress and served the same purpose. A chi-square goodness of fit test was the most appropriate tool for our project, since we wanted to test stated frequencies. We took a sample of 21 speeches from a population of all 228 State of the Union addresses. Each speech was assigned a unique number from 1 to 228. A random number generator was used to select 21 unique random numbers from this interval. The speeches corresponding to these numbers were included in our sample, which gave us a sample of 749,271 letters. We chose to cluster the letters in our sample according to their speeches, since it was impractical to do a simple random sample of letters from all 228 addresses. The cluster sample was random, and all expected counts were greater than 5 given our large sample size. Because we only sampled 21 clusters, it is reasonable to assume that our sample size is less than 10% of the population size of letters in all the speeches. To determine our sample frequencies, we used advanced technology, Google, to count the relative frequencies of letters in each speech. After comparing these to the sample size, we could determine the relative frequency of each letter in our sample. As expected, E was the most common, and Z was the least common. For our chi-square goodness of fit test, we tested the following hypotheses and calculated our chi-square components. With 25 degrees of freedom, the test yielded a surprising chi-square statistic of 13,490. This gave us a p-value of 0, which led us to reject the null hypothesis. That is, we found convincing evidence that the letter frequencies in the State of the Union addresses are not the same as the frequencies predicted in cryptological mathematics. It's possible that our letter frequency distributions were not the same as Lewin's, because the distribution of letters varies between different forms of writing, such as poetry, essays, prose, and speeches. While the stated distribution of letter frequencies is for English in general, we chose to analyze a specific type of English writing, political speech writing, which may have its own unique letter frequencies. Our follow-up analysis showed that the letters H and W showed up much less than expected, and 2 sample Z intervals comparing those letters with the expected proportions did not include a difference of 0 as a plausible value. Thanks for watching. Here's a summary of our findings.
Glad you could come, Doctor. Hello. Right this way.
We've been intercepting radio transmissions from Moscow.
Computer can't detect a pattern, but I'm sure it's code.
Why is that, General?
Ever just know something, Dr. Nash?
Constantly.
We've developed several ciphers. If you'd like to review our preliminary data. Doctor?
6737 0316 39 42314 90289 499 936 934 937 8 936 512 506